We're about to dive into some fresh BC calculus material, and what we're going to take a look at here is parametric equations. And as I go through this series of videos on parametric equations, I'm going to be using the note packet that you see on the website, and that's going to give us a basis for learning the fundamentals of these parametric equations. Won't necessarily go into the depth of difficulty that the AP test writers might want to do it. Well, let's take a look at what a parametric equation does for you before we get into the nuts and bolts of working with one. Parametric equations will take, for example, in the case of this rocket flying through the air and then eventually crashing down in a fiery mess, it'll take that travel and break it up into two components. There's the horizontal component, the force that's making this rocket want to go this direction. But there's also a vertical component, the rocket pushing up into the sky as it's going along, and then of course eventually the gravity wanting to bring the rocket back down. So as this rocket travels, there's really two components to travel, the horizontal component and the vertical component. Those of you who've taken some physics in your life, this is really ringing true because you're constantly diagnosing motion as horizontal and vertical components. And parametric equations are going to give you an easier way to do that compared to the regular old equations that you've been working with for so long. So I've now transferred over to that note packet, and remember that you have the totally completed note packet online as well. And we start off, you can pause this and read these instructions if you'd like, but I'm just going to hit the highlights. We have a curve defined by this set of parametric equations. Now we could rewrite that as x of t equals 2t plus 1 and y of t equals 1 minus t, and have the set of parametric equations look like that. That's also fine. And then we have a domain from -3 to +3. So think of the x equation as the equation that governs travel or location, in this case, left and right, and y is the equation that's going to give you a up and down, a vertical location. So let's just take any one of these spots in time. Let's take t equals 2. If I take t equals 2 and I plug it into these two equations, x of 2 is 2 times 2 plus 1. That means I get a 5 there. I take t equals 2 and I plug it in, 1 minus 2, that's a -1. So what this is telling me, at time t equals 2, I have a location of 5, -1. That's at time t equals 2. I could go forward 1 second in time and plug in, I'm going to do a little mental math here, that'd be a 7 and a -2. That means at t equals 3, I'm at the location 7, -2, and there's my location. Now I can do that for all of these times. I'm basically filling out a t-chart, but now it's a little bit more advanced t-chart. One equation gives me my x-coordinate, the other equation gives me my y-coordinate, and if you take the time to fill that out, you get that. Not very impressive in this case because it's just a line, just like good old Algebra 1. Well, a couple of things. If you're ever needing to go ahead and graph these, one thing that the AP test writers would want you to do is put in arrows to indicate the direction of travel or the direction that the curve is progressing as the parameter, in this case time, moves along. So there's nothing very difficult about graphing anything in parametric equations. And in this case, we got the very underwhelming result of a line like you would have had in Algebra 1. So then what we need to do is figure out, okay, if I can graph these, and I can graph these in parametrics, is it possible that I can come up with the rectangular equation, otherwise known as the regular old equations that you're used to, that would also illustrate this same scenario? In this case, you could probably break out your y equals mx plus b and get that done, but let's say you couldn't do it because it was a little bit more complicated. So what we're going to do here is this thing called eliminate the parameter. So how is it that we can take this set of parametric equations and turn it into a good old-fashioned y equals equation, or a rectangular equation? It's going to turn out to be just a simple endeavor in algebra, but I guess it could get kind of tricky. So a little vocabulary here. The parameter in this situation is t. Time is the parameter that is defining both our x location and our y location. That's why they call them parametric equations, because there's an outside parameter determining your x and y values. Well, if I want to turn this into some version of y equals blah, 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 which is fancily called eliminating the parameter, I'm going to go into this, in this case, this algebra technique of substitution. I look at this and I say, hey, if y equals 1 minus t, couldn't I also rearrange that and say t equals, let's see, don't screw this up, move the t over, 1 minus y. And if t equals 1 minus y, couldn't I take that and substitute back into that equation? Why, yes, I could. So when I do that substituting, instead of saying x equals 2t plus 1, I can say x equals 2, replace the t, and notice already I have eliminated the parameter. I have just simply x's and y's floating around in here. The parameter t for time is now gone. So technically I've eliminated the parameter, but I know you all have OCD tendencies and you want to turn this into y equals mx plus b, so I'm going to pause it and do that. We have done it. We have eliminated the parameter. We end up with y equals negative 1/2 x plus 1 1/2. And if I go back to the completed notes in the graph that we have, see if I can get these both on the screen, sure enough, this parametric equation is also the same as that rectangular equation. I have a y-intercept of 1 1/2 and a slope of negative 1/2. So that's the fundamentals that you need to learn today. The next example that I'm going to go over and just hit the highlights of is going to take the same thing in just a slightly more complicated scenario. I'm now on the second page of the notes. I have this set of parametric equations. They're, in this case, defined again by the parameter t for time. And if I take these equations and fill out a table, I can find my x and my y location at any spot. I can go ahead and graph that. Turns out that this set of parametric equations defines some sort of quadratic. In this case, it's opening up to the right. Notice I have the arrows on there to indicate the direction of travel. Well, the other thing you can do, since we figure this is a parabola opening to the right, you can take those two equations and you can use some algebra trickery to eliminate the parameter t. Same thing as I did, same style as before. In this case, my y equals 2t, or t equals 1/2 of y. So I can take that, plug it back in, and I get, in this case, x equals 1/4 y squared minus 2, which from Algebra 2 is, from the family x equals y squared, it's a parabola opening up to the right. That concludes our brief introduction to parametric equations. There's more to come. See ya.